lecture and share the screen. Okay, so let me see how many people are here. Uh, everybody here? Okay, so at the beginning, I want to uh, spend a few minutes to discuss about the most important things for this class, uh, including final and the term paper presentation and so on. All right, so if you don't mind, okay. All right, so I did a little bit study on on our calendar, UCR calendar, and if I am correct, our final week will be the week of December 14th and to the December 18th, right? Okay. So, because in the past, when we can go to the classroom on campus, so we need to follow the exact schedule because of the availability of the classroom for the finals, right? But here, so because we have everything online, um, so it's kind of very flexible for us. So I will ask you. So do you want to take the final exam on Tuesday or Thursday? Which is Tuesday will be December 13th and Thursday will be December 15th. So which day do you prefer?
Um, before, sorry, could we, uh, do we have a specific time frame for the exam? Like, does it have to be in, before you had mentioned that it would take about 2 to 3 hours for the
Yes. So
final.
yeah, right.
But because
Good question. Yeah, go
um,
ahead. Sorry.
I don't think that we would have to TA for that session, but maybe we have like other exams. Like I know if I take it
Hmm.
Thursday, I will have to be present for another exam following
I
that.
see.
So I wouldn't like have to three
Okay.
complete hours.
Good.
Is it
Very
possible
good
to
question.
give us? Yeah,
Yeah.
yeah.
Sorry.
Please go ahead.
Sorry. There's a like a delay. Go ahead. Please finish your question. Sorry
I
about
was
that.
wondering if like we could have a period of time so that we could like maybe 24 hours, and inside the 24 hours we could pass the exam during 2 to 3 hours when we logged in, like something like
Oh,
that.
you mean we everyone take the exam at the different time? You mean?
Yeah, we did something like that for the spring quarter.
Uh, so you so 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 that might be a problem for me. So that means like I have to stay online for 24 hours. Uh,
No, no, no. Yeah, I understand. Maybe.
uh,
Yeah.
so yeah, this is a good question. So I don't know if this will be a issue for us, but let's see. So usually um, uh, usually the arrangement for the final is like so if for a class you're gonna use the exact lecture time for the final usually. So our university just arrange the finals for every class like this, so there won't. But let me know if you so for example, if I understand correctly, you will have another exam on Thursday, so maybe Tuesday is better for if 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 this is not the case for other students, so maybe we can use the lecture time on Tuesday to take the final, which means we can start a little bit earlier, like maybe we can start from like 9 o'clock to the 12th. I don't think, yeah, it will take that long. So trust me. So although the stuff we're learning is tough, but the final will be easier, much easier for that. So it takes so if you are very familiar with the stuff, so probably like less than an hour you can finish everything. But please, yeah, figure out what your other finals exams will be. So let me know if Tuesday morning 9 to 12 uh, is good for you. So if not, Panya, so we can figure out a way. So, but it's okay. So even this is the only option. So I have to stay online for 24 hours. I will do that for you, for
No,
all of you.
I think like for that quarter, the class was there were like 100 students in the class.
Uh-huh.
It was an elective course, so maybe that is why the professor could do that. Because we are like eight, only eight, maybe a real-time exam would be better. Yeah.
Okay, so I will put this in my mind. So this could be a problem, but yeah, please figure it out. Let me know if you have any like conflict in time on Tuesday. If not, if this is not a good timing for everyone, so we're gonna figure out another plan. Is that okay? Is it okay to everybody?
Yes, thank you.
Yes, that's okay.
Yes.
Yes. Sure. Okay. All right. So okay. So now the final. So I'm gonna before let's see. So my plan is like so I hope everybody has already studied your research on the term paper. So please follow the template I provided, and the due date for the term paper is December 8th, which is a Tuesday, I believe. Let me see. Tuesday. Oops. Yes. Okay. And so our plan is like so. So the paper is due on Tuesday, December 8th, and then we can use the lecture time on Thursday, which is the December 10th. So in the morning, so we're gonna have a group presentation. So each student will have like 10 to 15 minutes. So you can present your small term paper, and then each one has a 5 minutes question and answer session. So yeah, please, yeah. So present. So when you present, do your best. And if you are listening to others, try to find some questions to ask. So this will give you some bonus points to boost up your final grades. Okay, yeah. All right. So that's for the Thursday morning, and so before that week, which I mean the weekend before the December 8th, I'm gonna upload a practice test to the iLearn, so you can have time to practice, and you can understand what you what you will see on the real final exam. And then so on Thursday, December 10th, so in the morning we're gonna do the presentation, but in the afternoon we're gonna use the discussion session to discuss the practice test. Does everyone has other obligations in the afternoon of December 10th, Thursday? I know some students probably have a TA obligations. No? Okay, cool. So then we're gonna use
time on December 10th, you said?
Yes.
Okay, double checking.
Mhm.
Thursday at what time?
So 2:30 to 3:30.
I don't think that's gonna work for me.
It's not gonna work. So how about 2 to 3? So does that work for you?
Is it possible to have it like 3 to 4? Because I have class from 1 to 3.
Yeah,
And
I'm okay. So how about you, Ryan? 3 to 4 on Thursday?
I TA from 2 to 3 and then 4 to 5. So my
Oh, okay. 3 to
slots
4.
are
Yeah, it's
before
very
those
stressful
times
for you.
or right in between. Yeah.
Okay, so yeah, I think probably yeah. So you won't. I don't think it will take long. So so yeah. So let's plan on 3 to 4. Okay.
Yep.
okay, thank you.
Sorry, I have meeting in 3:30.
3:30. Okay. So yeah. So don't worry. I try to finish everything in 30 minutes. So because it won't take that long. Because if so, as I mentioned, for the final, if you are very familiar with the stuff, you take like less than an hour to finish. So for me to go through the practice test, I think, yeah, 20 minutes is enough. So yeah. Okay, so let's plan on 3 to 3:30. Is that okay?
Okay.
All right, so yeah, I'm gonna go over the practice test within that time frame. But in case you need additional time to discuss some questions, so you can send me email. We can schedule a one-to-one discussion. Okay. All right. So yeah, it's pretty good. So everything seems to be yeah settled. All right. So let me see. And so for the final, I think we have already covered the majority of the stuff. I think it's most important for you, which is the stuff from chapter 1 to chapter 9. So that's the very important basic thing. So you're gonna see on your final exam paper, like 80% of the stuff will come from chapter 1 to 9. And that doesn't mean that today's stuff is not important. I still hope you treat them equally. So because it's important for your future research. So today we're going to talk about something different, but it's very useful. And so I have already uploaded everything, lecture notes to the iLearn. So as you can see, so for the later chapters, it's all about applications. So that's why we can go very quickly. But we pay much more attention on the previous chapters, 1 through 9, because those are the very fundamental, important concepts. So yeah, that's the focus. Is that clear? Yeah, you're gonna see that when you look at when you see the practice test. So yeah, you're gonna see that the breakdown. Like 80% of the stuff is before it is from chapter 1 through 9, and only 20%. So for the later part, the 20%. So I mainly focus on like concepts. I will not ask you any questions about like calculation, like show me the derivation, so which is too complicated. No, but for the later part, maybe 20%, I will put some questions to test the concepts, logics behind some questions, problems. Does that make sense? Okay. Any questions about this arrangement?
For the presentation, would you give us a rubric to see how you'll grade us for it?
You mean the practice test?
No, for the presentation.
Oh, presentation. Oh, you mean the deadline for the breakdown
Yeah.
points? Good point. Yeah. All right. I didn't do that before, but yeah, this is a good suggestion. So
Okay.
let me think about this. Maybe, yeah, I will propose a plan and post that on the iLearn, so you can give me feedback if you like it or not. Okay. Yeah, sure.
Okay, thank you, Professor.
Yeah, but the one thing I would like to strongly recommend is like when other students is presenting. So please, yeah, don't just think, yeah, that's none of my business. So pay attention and try to ask questions, because this will probably your grade will be A, but this will make you this extra bonus will make you get an A+ or something like that. All right.
Okay, thank you.
Yeah, this is a graduate level class and relatively small classroom. So usually I'm very generous to the grades. So but yeah, you can do your best to make it better.
Thank you.
Okay, sure. Okay, let's see. So if you do not have any other questions about the finals and the tests, so let's continue. I'm gonna turn off my, oops. Let me turn off my video and start sharing. Okay. So last time we learned how we can use what we have learned to do the entire genome scanning, right? So even we may have like very sparse markers on the genome, for example, like this, but still we can use the so-called internal interval mapping, not internal, interval mapping to help us to infer the genotypes in between two markers, right? And then we can test everywhere on the genome to produce a very smooth curve for the test statistic. And this can help us to identify the genomic loci, for example, here, showing the strong evidence of the association with the phenotype of interest, right? So this is a very useful method, tool that probably you're going to use some of this in the future to help you to identify some interested genomic loci, and then you can dig in to zoom in into this region to identify some probably new genes, and name that genes with your name proudly, and then so contribute a lot to the science. So this is the GWAS, so or QTL mapping. So in the QTL mapping, we can generate two kind of plot. So the first plot is the Manhattan plot. So I didn't prepare a photo for the Manhattan, so it's so beautiful. It's just look like this. So that's why we named this plot as a Manhattan. Okay, so and you can also generate something like this. This is the plot that you can use to estimate the genetic effects, either the additive effects or the dominant effects for each locus, right? Something like this. So this is negative, which means like this is positive. Okay, this is what we have learned last time, and so if you think about this, so we used to, so we in the past we only consider the phenotypes, which is a quantitative phenotype, which means like this phenotype is so the measure of the phenotype for each individual is a continuous variable. For example, like the height of the people or the yield of different rice variety. All right, so that's a quantitative traits. So today we're gonna learn something different. So we're gonna use the interval mapping or GWAS to help us to identify the genomic loci that are associated with the categorical variables, response variables, or ordinal, or something that is different from the quantitative traits, the numerical traits, right? So for example, the eye color, this is an example for the ordinal traits. So we cannot use any numerical numbers to represent each color, right? Because that numbers cannot represent the difference, the real difference between different categories. So we cannot do that. So this kind of traits is called the ordinal or categorical traits. For another example in medicine is like the smoking status, smoker or non-smoker. That's another traits, ordinal traits, or cancer. So the normal and the cancer, that's the outcome for a subject. So that's another example showing the ordinal traits. All right. So for the ordinal trait or the categorical trait, so the commonly used method is to use a regression called the probit regression. So this is a little bit different from what we have learned before. All right. So for example, let's talk about the example in medicine. So cancer. So suppose the Y is the real disease phenotype. 1 means cancer, 0 means normal. So this is what we can observe. This is observed. But actually, there's a latent variable, which is Y star. so which we cannot observe. So this actually is a latent variable that determines the observable y variable. So for example, if this variable, the latent variable, is greater than 0, a cutoff, then this individual will show the cancer phenotype. Otherwise, if this variable, this latent variable, is less than 0, this will not cause cancer, and then this subject will be a normal in terms of the cancer. So is that clear? So here, oops, discuss this. So basically here, because the observable phenotype falls into two categories, cancer or normal. So this is not continuous, right? This is not numerical. This is not quantitative. This is qualitative or categorical. But actually, underneath this categorical variable, there is a continuous variable. So this Y star actually, although this cannot be easily measured, but this is a variable controlling the Y, the real Y, observable Y, and the Y star is actually acting like a quantitative trace, just like the yield or the human height, right? So, all right. And if this is the case, we can use this linear regression model so to model this unobservable Y star. And we can use this regression coefficient. So this is a regression, and the beta here probably can include the environmental factors and the genomic factors. For example, the genotypes, information about any locus that need to be tested. And okay, so this is the random error. But in this probability regression model, so we always assume this random error is normally distributed, standard normally distributed, with the mean equals to 0 and the variance equals to 1, because this is an disadvantage for this study, because the variance of the residual cannot be estimated correctly because of the entangling. So that's why we always assume, so the variance of this residual error is equal to 1, which means this is a standard normal distribution. Okay, so if you have questions, just let me know so we can stop anywhere to answer your questions. Okay, so this is the basic setting, and so now we can actually define this, because so the Y star, if Y star is greater than 0, then the Y equals to 1, right? Otherwise, if the Y star is less than 0, so Y equals to 0. And so we can translate this, because of this relationship, we can translate into this. So when this holds, Y takes the 1 value, but if this is not holding, this is not true, so then Y equals to 0. And okay, so this is associated because the error is a standard normally distributed random variable, so we can associate this with the standard normal distribution. This is a standard normal distribution, and if we do some like math, we can find the probability that given for any individual patient or for any individual subject, human being, if the predictor variables, including the genotypes at a locus, given this information, so what is the probability that this subject will carry a cancer? So that's the probability. So if you do a math, so you can find this probability equals to this. This is the CDF, the cumulative distribution function for the standard normal distribution. And yeah, it can translate into this diagram. All right, so this is the patient. For this patient, you can calculate this value, and the curve and the standard normal distribution on this side is the probability that given this genomic information or environmental information, what's the probability? This is the probability. The area under the curve on the left is that the patient will have cancer, and this is the probability. On the right-hand side, that's the probability that given this information, genomic information, this patient, this individual is a normal one. So is that clear?
What is the,
Mhm.
sorry. Yeah,
Yeah,
what
go
is
ahead.
the pi denoting in the last line?
Say that again, I'm sorry. This one?
What is the pi? Yeah,
Oh,
yeah, okay.
fine. Yes, okay, sure. So when we talk about the standard normal distribution,
Mhm.
we use little phi. This is little phi. This is big one. This is big phi. Okay. The little phi is the probability density function P D F, which is defined as something like, I don't remember. So maybe 1 pi 0 something like this. I don't quite remember.
Okay.
So yeah, that's the density function.
Mm.
Okay, the x beta, y minus x beta or something. Square. Okay.
Okay.
That gives you, this is a PDF function, right? That gives you a specific value, the height of the curve. That value equals to this.
Oh.
Yeah. Okay, now the big phi is called the CDF, the cumulative distribution function, which means still associated with this PDF, because we want to look at the area under the curve based on this value. What is the area under the curve? So that's the cumulative distribution. Yeah. Okay. So that's the big phi.
Okay.
If this probit regression is similar to the logistic regression,
It's
or-
very similar. So yeah, we're going to talk about this shortly. So yeah, it's I can say it's like equivalent, but sometimes like there's a small changes. But yeah,
okay.
the logistic is the logistic. No. Logistic is not this. Logistic is not this. But the liability function is equivalent to the
Okay.
to the probit regression. Logistic is a little bit different because that's also like exponential family density function, but it's different from this one. Yeah. Okay. Yeah, we will talk about the logistic. I think at the end of this chapter. All right. So, any questions on this slide?
Just to review, in terms of not changed, beta is still our cumulative, like Z, and it's still
Right.
our Z and W, and X transposed version is still our genotypic values.
That's right. So here I just copy and paste from the website. So actually this is the whole thing. But if we can think about this is the sum of the environmental factors and the genomic factors, the sum of this. So then we can say, okay, so we can use this. For example, in the past, we use X transpose beta to represent the environmental. For example, whether this variety are these varieties are planted in the United States or in China, right? So we can use this to represent the experimental, but we can use Z, gamma, and W, or we can use A here and dominant here to represent the genomic effect, right? So the whole thing, we just use this thing to represent the whole thing. So this is what we commonly used in our previous analysis, right? Linear regression.
Yes.
So now here, so because I only copy and paste from web, so this thing represent the sum of all these things. Does that make sense?
Yes.
Okay, now if we can use this to do the test, so we are only interested in the genetic part, so we can only estimate the additive effects and the dominant effects, and then we can test on these two effects to see if this locus is associated with this categorical response variable.
Okay.
Make sense?
Yes, makes sense.
Great. All right. Okay. So all right. So then we can. So here we only have like two categories, right? Two categories: the cancer or normal. So sometimes we have like more than one categories, more than two categories. Sorry. So for example, the eye colors, we may have like 6 or 7 different colors of the eyes, human eyes. Then we're going to use the generalized linear model to to deal with this problem. So suppose we have like p+1 phenotype categories. Right. So this is the categorical phenotypes. All right. So we cannot use the numerical number to represent them, but we can label them. So we have like p+1 category, and we use an indicator variable s. So if this s equals to k, means, all right, so this is the case, k is a number between 1 to the p+1. So if this indicator variable equals to k, means, okay, this individual, J's individual, came from the case category. So is that clear? Okay. Just so we use these variables to just to facilitate our presentation. All right, and all right, so we have a y. So this is the observed data for a individual J, for J's individual, and this is a vector because we have like, oops, sorry, power low. Okay, because we have p+1 categories. So for each individual, we use a vector to represent the y. Let me show you. So there's no space here. So the y means, okay, this is a vector. So we have a vector of length of p+1. And so for this J individual, we have like p+1 numbers, scalars in this vector. So if this one belongs to the K category, so only the K is scalar equals to 1, but the other place will be 0. Does that make sense? We use this vector to represent the observed categorical phenotype for the J's individual. If this J's individual shows the eye color in this category, so only this category we use 1, we put a 1 here. So because this individual do not have other colors, so we put 0 everywhere else. Does that make sense? That's your y variable. It's a vector. All right. So for each of this, so the y has so for each scalar in this vector, so we use this to represent either equals to 1 or 0. Okay. So now the expectation of each element in this vector will be this. So we use mu represent the expected value for any single y, jk, and this is the expression. So why is that? Let me show you. Why is that? This is, yeah, when you first look at this is horrible. But still, this is the CDF function for the standard normal distribution, right? So let's see why this looks like this. So if we look at this example here, okay, so we're gonna extend our binary response variable to this more than 2 categories example. So suppose in this case we have 6 categories, 6 eye colors, right? So how can we treat this? So how can we treat this 6 categorical problem by extending the application of the binary response variable. So it's very easy. So this is a very creative idea. Actually, in science, in science, you will find a lot of fun. So when you try to do some research and come up with some creative idea. So in this case, if we treat the category 1 as a single category, and we group 2, 3, 4, 5, 6 together, then this is a binary problem, right? So in this case, I just show you probability that y equals to 1 given x equals to what? Equals to the big phi, which is the CDF normal distribution of x beta, right? Do you still remember in the first slides? All right. So now if you group 2, 3, 4, 5, and 6, then the phi 1 will be equal to something like this, right? Okay. Phi 1 is the area actually in this area, right? Okay, next, we define this as phi 1. How about phi 2? When we do the phi 2, actually you group categories 1 and 2 together, and you group 3, 4, 5, 6 together. Then the phi 2 will be equal to the area under the curve, like here. Is that right? Including area 1. Then how do you calculate the area of 2? That's easy, right? If you want to calculate the expectation value of the mu2, which is the area number 2, then you simply use the phi 2 minus phi 1, because phi 2 is the area under the curve on this side, which include area 1. So if you remove minus the phi 1, then you can easily calculate the area, the number 2, right? Is that clear? And you can also do the same thing, extended this thing. So how can we calculate the area in 3 here? So you just calculate, calculate the whole area on the left and minus this. So you got the area 3. So that's how you calculate the mu3. Mu3 actually equals to phi 3 minus phi 2. So you actually formulate this multi-categorical problem by the application of the binary response variable problem. Is that clear?
I have a question.
Yes, sure.
So for the category 1, mu1 will be equal to phi 1, right?
Mm-hmm.
Okay, that was my question.
Yeah, the phi 1 is actually the area. That's easy. That's simple, right?
Okay.
Yeah, the phi 2 actually is the area on the left of this line. So including phi 1. So if you just want to calculate this area, which is the expectation value of the E, Y, J2, we use mu J2 to represent this area. And that's easy, right? You just use this difference. And okay, so this is how we calculate each mu JK, the expectation of each Y, and it's actually use the area minus the area before that one. Does that make sense?
Yes.
Okay, so let's go back here. So, all right, so this is how we define the formula to calculate the expected value for each Y here. So this is, so I don't think like there's in the textbook there's a derivation for this. Dr. Xu just used this formula as a fact, but how do we understand this? So yeah, this is the way. So we can use this logic to help you to understand why this is this is the calculation for this expected value, right? And A0 is the minus infinity, and sorry, alpha 0, alpha p plus 1 is the positive infinity. All right. And okay, so now when we get this, so this is still a vector, right? This vector includes like a p plus 1 mu's. Sorry. All right. And so then we can easily formulate the variance of the y. We have the expectation of the y. Now we can calculate the variance of the y, which is equals to this. This is the matrix notation. Yeah, don't worry about this. So from now on, so all the calculation is not relevant to the final exam. So just for your information, but you should be able to understand this, because we have learned how we calculate the variance of a random variable, either in a scalar format or in the matrix format, right? Okay. All right, so now once we have this, so we can calculate the variance of the y. But here, because this calculation involves like the inverse of a matrix, and because of the rank of the matrix is not full, so we have to use some very special technology to do the inverse calculation of the matrix. But it's okay. So you just know this. You don't have to understand understand the details about this. Anyhow, so even this matrix is not a full rank, so we still can calculate the inverse of this matrix, and this can help us to estimate the parameters. So in this case, we have these parameters, right? We have the beta and gamma. Gamma is the genetic effects for any locus, and this is the intercept. So I just show you here. So this is the intercept. Also the parameter we need to estimate from this model. All right, and so now it's easy to still use the binary data to understand how we derived the solutions and the variance for the estimation, and then how we can use this calculated value to do the test. All right. So as you can see, so this is the way we calculate the expected value for y, right? We use the CDF function, but this function is not that attractive for solving the parameters using the MLE. So what we can do is like we can do the reverse inverse function, and once we get the inverse function, we put a y star here. Then look at the right hand side. Oops. The right hand side is a beautiful linear regression model. So then we can use this to easily derive the likelihood function. And then we can do the first derivative and the second derivative to find out the solution for those parameters. And then we can do the test. All right. So don't worry about this. Although this is complicated, but the basic is very similar to what we have learned before. Because here we use the inverse function of the CDF, right? This cumulative distribution function for the standard normal distribution. So in the past, we just use a simple linear regression. So here we still use an inverse function, but the inverse function is for the identity function, which means identity function means just this guy. We use this guy to do the regression. So that's the simplest version of the inverse function. But here we just extend this inverse function to the CDF, the cumulative distribution function for the standard normal. All right. Any questions here?
Yes.
Yeah, go ahead.
What is this identity function?
Oh, identity function. So, okay, identity function means y equals y. So for this function, if you input y, it will output y as well. So that's the identity function. So that's why if we do the inverse identity function, this will gives you the same thing, right? In the past, we use a linear regression model like this. So that's the same with this, right? Because we use a inverse function of the identity function. Identity function is itself. But here, since we do not use the identity function, we use a inverse function of the CDF. That's the difference here. So I try to link the current model with the model we used to use in the past when we just used the simple linear regression. So they are the same. So in the simple linear regression, we can still treat like that regression is using a inverse function, but the inverse function is of a very special function, which is an identity function. So that's why you do not see any difference. But here, if we use the inverse of a non-identity function, which is a CDF here, then maybe this will scare you away. But actually, they are the same. We just use different. We just use the inverse of different functions here to do the regression. Does that make sense?
So the inverse of the CDF is what we use for regression.
Yes, because here, this is the relationship. Erase this. So this is the expression for the expectation of y, right?
Mm-hmm.
Equals to this. But this is a CDF function, which is very complicated. So if you use this CDF function to do the MLE, so that would be a horrible dream for you. Okay, so that's too complicated. But if we use the inverse of this, then this becomes a linear regression. Then based on this, we can easily formulate a likelihood function to continue your maximum likelihood estimation calculation.
Okay. All right. I'm following.
Mm-hmm.
Can you
Great.
explain what's the beta and what's the alpha?
Oh, the alpha. So here,
What's the parameters represented?
parameter. Yeah, this is specifically for the probit regression. So here, this is the simplified version, right? If we, so this is actually equivalent to this. Is that right? In this case, specific case, alpha equals to 0.
0.
So that's why, so you compare the whole thing with the alpha, right? So in this case, so we still compare the whole thing with this alpha. But now this alpha is not equal to 0 because we have more than like 2 categories, right? Something like this. Yeah. So that's the specific parameter. We also call this alpha as an intercept for the probit regression.
But so for beta and gamma, that's gamma. So gamma is the genetic.
Yes. Beta is the non-genetic factor.
It's like the intercept, or I'm not sure.
This is not intercept. So if it is intercept, it means like still. So this is the intercept, which means this thing is a constant for any individual, right? But why we have this term? Because maybe you do a large scale study, you include like data from China and from US, but you believe there's a systematic difference between the data from China and the data from the US, then you have to use this to model the difference between China and the US, right? But that's irrelevant with the genetics. So that's why we need additional term to represent, to model the genetic effects from any locus.
Okay.
Yeah. So for example, if this is the yield for a cultivar, so we can say, okay, so this is the beta 0, which is alpha. So this will be the intercept, and this will be a constant. This will be the same for each individual cultivar, right? But now we use XB1 to represent either, so maybe 1 equals to China, 0 equals to US.
Okay.
Then this will represent the systematic difference from these two subpopulations. And then we can plus the thing we are more interested in, right? Let's say Z additive, so beta 2 and plus W D, right? Because we want to test on these two things. That's the linear model. So the same with this.
Okay.
Okay. Okay, let me see. Okay, what time is now? All right. So then, so once we have this setting settled, then we can use our old business, old schemes to do the analysis, right? So here we construct a likelihood function, but this likelihood function is based on the multi-normal distribution. So this is, so I don't want to go too deep, but if you are interested, you can look read the textbook to make yourself understand why we construct the likelihood function using a different way. So this is the multi-normal distribution. And okay, then we can easily do the first derivative and the second derivative to find the estimation for the parameter and also the information matrix, right? Okay, so in this case, we have two kind of situations, two models. So first, the maximum likelihood model and the homogeneous variance. What does that mean? Homogeneous means like we assume, so every individual will follow a normal distribution with the same variance. So why is that? Because if we knew, so this go back to our previous knowledge, right? So in the past we learned the problem, the complete data problem. So when we have the complete data, so everything is observable, then that's easy. So we do not change the probability model. But sometimes, so for example, in QTL mapping or GWAS, if you only have the genotype data for the markers, so what if you want to test some genomic region without markers or between two markers? You do not have to observe the genotypes, right? Then you have to infer the genotype for that locus using two flanking markers or using other markers. Is that right? This is what we have learned. So okay, so this is the formula for the complete data. If we can observe the genotype of that locus, that's easy. And in this case, the variance equals to 1. Okay, standard normal distribution. However, if the genotype of this locus is not known, so we have to use the expectation to replace this Z, to put you here, right? Then this will make some changes. We have learned this before, because if you use the expectation, which is different from the real Z, so then you're going to introduce additional error into the model, and then this will change the variance, the assumed variance. So in this case, the variance is not equal to 1 anymore. So the variance, if you use the expectation value of Z to replace the real Z, the residual error variance is no longer equal to the unity, which is 1. So it's no longer equal to 1. But if we assume, a homogeneous variance, even it is not equal to 1, but if the variance is the same across all the individuals, then that's not a problem. We can still use the formula, the complete data formula to do this, but we have to use the mixture model setting. However, if we do not assume that each individual has the same variance, so this means like the ML, the maximum likelihood model, is under the heterogeneous variance, then we have to estimate each individual variance for each individual. We have to estimate the specific variance for each individual. That's why, so if you compare this model with the previous model here, what's the difference? We have an additional term here. Why? Because this is not following. So for each individual, we have to standardize the residual error. So that's why we're gonna divide the whole thing in the original model by the residual variance, and to make sure that this distribution, the residual distribution, is following a standard normal distribution with the variance equal to 1, and then we can use this big phi function to calculate the probability. Does that make sense? So yeah, go ahead. Right.
I might need a refresher. So the 1 over the whatever that Greek symbol is, J.
Mhm.
What is the particular function of that in order to, that way we can infer a unique variance for each?
Oh, right. So first, we need to estimate the variance for each individual. Let's say this is for J's individual. We need to estimate these things first. Once we estimate this, we can adjust this. So we divided the whole thing. So this is from the original formula, right?
Yep.
We divided the whole thing by the standard error of this. Then we can make sure the whole thing is following a normal distribution with variance equal to 1.
Okay, so this is how we can actually assume that. So using this adjustment for a unique variance for every single one, now since we have done this, now we can assume n 0, 1, or a variance equivalent to 1, or a normal variance.
Yes, that's right. Yeah, that's the purpose for this. Because
Okay.
so this is very common scheme. So in the future, when you try some advanced model to do the GWAS, you're gonna see this quite often. We call this factor is a normalization factor. So we try to use this to normalize this guy to make sure the normalized the value after the normalization is following a normal distribution with variance equal to 1. So this is the scaling factor, or the normalization factor.
Got it.
Mm-hmm. Yeah.
So this variance is to the phenotypic value, to the variance of the phenotypic value, or the variance to the genetic value.
This is the residual value, So this is very special. So yeah, this is included in the genetic. Is not included in the genetic variance, but it's included in the phenotypic variation. So this model, so it's not it's not equivalent to the previous model. We used the simple linear regression. This is a probit regression. So yeah. So look at here. The first slide here. So we use this probit regression model, right? We have assumed this error is following a normal distribution, standard normal distribution.
Mm-hmm.
Okay.
So For general linear regression, do we not assume that the error follows a normal distribution?
Right. So usually, so that's a good question. So that's the difference between here we use where we use the probability regression, right? So for example,
Mhm.
if we use this simple linear regression model, that's B0 plus B1 X plus, let's say B2, oops, Z, okay? Let's use this, and then plus a error. So here, what we assume is this is a normal distribution, but we never, with mean equal to 0, but we never assume this is standard normal distribution. We assume this guy is a normal distribution with mean equal to 0, but with a unknown variance. So this is also a parameter which need to be estimated from your data. But now for the probability regression, this thing cannot be estimatable. So that's why for our convenience, we always assume this is a standard normal distribution. Okay. All right, is that clear?
Yep, thank
Mm.
you.
Okay. Okay, so now as you can see, we have we use a different thing, the scalar, the factor, the normalization factor to adjust the model because of the heterogeneous variance assumption, right? And then this will change the calculation. And so, yeah, don't worry. So we do not want to go deeper, but so we will change the calculation of the first derivative and the second derivative. And then finally, we're going to use the mixture model distribution. Why is that? Because we do not know the genotype data for the locus, right? So we want to estimate this. We want to estimate this Z given the marker information. So marker 1 and marker 2. So then based on the marker, so this locus can take 3 possible genotypes if this is a F2 population. And then this is what we have learned, right? So we can use a mixture model to help us to construct a likelihood function for the mixture model. And then, so this is the expectation step. We calculate the expectation, and then we can use the maximization, treating so once we have the expected value, and then for the missing value, we can treat the problem as a complete data problem, and we can use the closed form for the maximum likelihood estimation, and then we can do the iteration to do the calculation. Once the iteration, the EM algorithm converges to some point, so we can get the estimation for theta, and we can also calculate the variance of that, and then the life will become much easier for us. We can just construct like test the statistical test or chi-square test or F test or something to test whether the additive effects or the dominant effects at this locus is significant or not, right? All right. So this is actually the probability regression model is actually equivalent to the liability model. So we're going to also talk about this model in the next chapter. But here, so we're going to very briefly introduce this. All right. So here the liability is actually the latent variable. So I just mentioned, so Y star. And this is the real phenotype you're going to see. For example, the normal, this is normal, this is cancer, right? So maybe there's a latent variable, so called the liability is functioning behind or underneath this observable variable y. So if this value lower than the threshold, then this is a normal. This will give you a normal outcome phenotype. However, if this value goes beyond this cutoff, like here, so this will give you the cancer phenotype, the disease phenotype. All right, so we use this probit regression model, actually treat this latent variable here as a liability variable, and we use a liability regression model, which is equivalent to the probit regression model to help us to do the modeling. All right, so the same, this is the same here. So if we use like a binary situation, so we use 2 y's here, right, to set up a regression model. So here we set up a regression model here. So this is the latent variable here, the latent, and we use small y, the little y, to represent the latent variable, and we use the big Y to represent the observable outcome. So this will be, this big Y will either equal to 1, represent the disease phenotype, or 0, the normal phenotype. But underneath this big Y, there's a latent variable, liability variable, so small y. So we can use this linear regression model to model this guy. Okay, now, so yeah, this is a little bit different because here, so liability, if we use the liability model, so here we can assume this probability is a normal distribution with a unknown variance here. But as I mentioned, because this is a hidden this is a latent variable problem and liability problem. So at first we can assume this is a normal distribution with an unknown variance. But for the liability model, this sigma square cannot be estimated. So we always set this thing equals to 1 for our computational convenience. So this is what we use the probit regression here. Okay. Everything else is the same. Okay, now, if this is a complete data problem, in another way, so if this Z genotype at a locus and the Y, little y, which is the latent variable, liability variable, were both observed, then easy, right? So we can just use the MLE to estimate these 2 parameters. So that's easy. However, if we only observed the Y, suppose we could observe the little y, the latent variable, but we do not know the genotype. This is what we have learned, right? So we can use the marker to estimate this, and then we can calculate the expected value for this. Then we can use the EM algorithm. So each step we use the expected value to produce a pseudo complete data, right? So this is what we can do. But now in this liability model, so both things, neither of this and this, neither this nor this can be observed. So what should we do? So we can do the same thing. So we can plug the expected value for the Z, and we can also plug in the expected value for Y to complete our EM algorithm. So I hope that every one of you can appreciate the beauty of the EM algorithm. So if you are missing something, you just calculate the expected value for that thing and plug that expected value into the formula, and then you can use the EM to get the solution. Any questions here?
One quick clarification.
Yeah.
Z value means what in this overall equation?
What value? I'm sorry. Z value. Okay, Z value is the genotypes. So remember our in our previous simple linear model, we use B0 plus XT B1. That's the experimental, right? Non-genetic part. But Z times B2. So Z transpose. So Z we use so think about Z consists of two things. So consists of let's say W. I'm going to use another one. So think about this as a so we use Z to represent little z to represent the additive. We use little w to represent the dominant. Do you remember that?
Yes.
Okay, so if we put this little z and the little w together to form a big Z, that's the genotypic information for that locus, which we want to test. Does that make sense?
Yes, but we just talked about how X is also the genotypic information, which is thrown.
Oh, no, this X, right? No, this is not. So this, suppose your data came from two locations, China and the US. So this X just shows you whether this data came from China or US. So this is non-genetic part. But because the data is a combination of two data sources, we have to address that because there's a systematic difference between China data and the US data, right? That's due to the environmental, not the genetics. So, but we have to put this in the model to make an accurate estimation for the genetic effects.
So X is suddenly our environmental value.
Yes, yes. So in the future, so probably when you become an expert in the quantitative genetics using GWAS, so you probably can help John Taylor to analyze his data. So he has like two data sources. So one is the growth in Riverside, and the other one is in Santa Barbara. I believe there's another the pomegranate field, right? So so he planted the same genotypes, the same cultivars of the pomegranate into two different locations. You get the data. So you cannot treat this data equally, right? Because the environment in Riverside is totally different from, it's not totally, it's very, very different from the environment in Santa Barbara. And then, so how do we do that? So we are gonna use this to model the difference between these two locations. But this factors is irrelevant to the genetic effects. So we use this to remove the environmental contribution from the total phenotypic variation, and then once you fix this part, you can accurately estimate the real contribution from genetic part. Does that make sense?
Yes. However, the summary that you gave earlier in the lecture, summarizing,
You mean here, right?
R is X transposed beta plus variance.
Here, right?
Yep.
So here, because I mentioned it, because I copy and paste. So I just stole this equation from the website, because the website used the thing to represent the whole thing. So you can treat this, so the whole thing as fixed effects plus the genetic effects. So the whole thing represented this thing.
Okay.
Use different notation because I don't want to change it. This is what I got from the web. So they used a single thing to general term to represent. Actually here we have specific research goal, right? We want to separate the contribution from environment and the genetics. But here probably they do not have that many like factors. They just want to see if the factor of interest are contributing to the variation in the Y response variable.
Okay, making more sense now. Thank you.
Okay, good. Let me see. Where were we? So we are here. Okay, here. Okay. So I hope, yeah, this is clear. So the step by step. So if we can observe all the missing data, so easy, just use the maximum likelihood estimation, right? If we're missing one, we plug one. So no, if we are missing one, the genotype, we just plug in the expected value for the genotype data, and then we can still do the MLE. If we are missing both the genotype and the latent variable, the liability variable, you can do the same. So each step, we just plug in the expected value for both guys, and then we can do the iteration, and then we can get the solution. Is it beautiful?
I have a question
Mhm.
about the observed data. So
Mhm.
the observed data is a Y, is a capital Y, like the
Yes.
categorical
Yes.
data.
Mhm.
And then we use the capital Y to calculate the latent variable YG.
Yes.
Okay.
Yes. So this is the same here. So we use, let me see. The likelihood is here, right? So the capital Y here. So we use a multi-normal distribution to calculate the likelihood function using the capital Y. So using this, you can calculate the expected value for the little y. Okay, good question. So so is it clear?
Mm-hmm. Okay.
Okay. Okay. So all right, and then so we can use we can leverage the EM algorithm, right, to get the solution. So yeah, those are horrible formulas. I don't want to even touch this page. Okay, let's go further. So yeah, this part, yeah, it's easy, right? So for the EM algorithm iteration, we just initialize the parameters. So we give a legal. So every time when you try to run the EM algorithm, so don't test don't fit in a illegal value. So just give a reasonable value within the illegal within the legal range, and then this will make the EM algorithm converge very fast. Yeah. So and we can also use the Monte Carlo simulation method to do the same thing, like iteration. But yeah. So you can, if you want to learn more about the Monte Carlo method, so you can, yeah, go read the textbook. So it's related to the iteration, and this is the logistical analysis. So okay, let's come back to your question. I think, yeah, this is the last part for this. Yes. Okay. So all right, it's very complicated. So I just, yeah, I don't want to spend too much time and to go to the detail, but yeah, let's introduce this to you. Oops. Okay. So here we still use the exponential family function, right? So the logistical regression, the logistical analysis, so it's very similar to the probability link function, but it's not the same, right? It's not the same. So here we try to transform. So here instead of using the probability function as a link function, we use the logit link function to perform this generalized linear model. So we define this response variable using this ratio. Okay, it's very complicated, and as you can see, this is an exponential family function of the. This function is also from the exponential family, right? And here, this is the key part. So here we still see a beautiful linear regression here. So we want to use this still use the inverse function here. So where is the inverse function? Okay, yeah, this is the logistic logit function to do the inverse function. And then what is that? So you can end up with a beautifully defined linear regression. So the trick is here. So we use this kind of specific modeling, which is called the logit function. And when we get the inverse of this, we can also get a linear function. Once you get this linear function, we can use the observed y, which is 1 or 0, something like this, categorical data, to construct a likelihood function using this observed y and this linear regression, and then we can still use the MLE to model this situation, and then we can use the first derivative and the second derivative to estimate those parameters and the variance. Then we can complete the test for each locus. So is that clear?
No, why are the exponential variables there?
Oh, okay. So this is a, let me, okay. All right, just think about this. So this is a very special setting. So when we look at our own problems, do you still remember this? The mu equals to this x beta plus z gamma.
Yes.
So I write this model simply like this, but if you want to express this will involve exponential density function, something like this. So this expression is even more complicated than this one. So if you want to expand this function, so the expansion of this function will involve the exponential as well, because that's the part of the normal distribution, right? I just wrote this model simply using this simple formula, and yeah, so that's why it's easy for you to understand. So we have an exponential here because the exponential, this function, either this function and the normal distribution, both of them belong to the exponential family function, and we use this specific way to model this y, this variable is because this variable is following a distribution like this. So okay, sorry, not this one. So the exponential distribution itself is following like this, right? So the range of this is what? Is let me think. Exponential distribution is like this. Yes, 0, 1, 0 is okay. So this is the distribution of the exponential, right? So what's the range for the exponential variable? What's the range?
0 to
infinity, right?
Mm-hmm.
Okay, very good. So let's see this ratio. So when this thing takes the value of 0, what is this? 0, right?
Mm-hmm.
So if this thing takes the infinity, what is that? That's 1, right?
Yes.
Yeah, that's very similar to the range of the probability. Is that right?
Yes, it is.
Yeah, so we use this very special setting to model the probability between 0 and 1. So then you can see this 0 to 1 distribution of this thing. This is equivalent to here. Something that this is the connection between this to this. because the area under the curve of the normal distribution is 1. And any probability for this area will change from 0 to 1. So this is how I can explain why we use this special setting here, because this is a smart setting, I can say, because you can translate. So for example, the domain for X, the initial thing. So for example, the initial thing here, the domain for this is from minus infinity to infinity, right? So look at here. So this is the domain for the parentheses. And if you use the exponential, this will change, this will make the y, let's say y is the whole thing, exponential. The domain for y will be 0 to infinity. And then if you use this ratio to define this parameter, this will give you a 0 to 1 domain, which is a perfect domain for describe a probability, the range. And then you can use the expected value mu. You can express the expected value for mu, which is the thing of interest, right? By using the difference between this one and this one. This is very similar to here. That's the connection here. Does that make sense?
Yes. Yes.
Mm-hmm. It's very similar, but using different function here. So here we just use the okay, sorry. Discard this. So for the logistic regression, we use the function called the logit, but for the probability function, the previous one, the liability probability, we use the probit function. Very similar. We use this to get the linear regression, and then we can easily use this regression setting to set up a likelihood function, and then we can get the MLE. All right, so yeah, it is very complicated. So I think, yeah, so if you want to better understand this, so maybe we should read more stuff about this. But I don't think I have time today to do this. And this will not be required. This will not be required for the final exam, just for your information. So as I mentioned, from now on, from chapter 10 and on, we mainly focus on, so even I introduced some like very complicated derivation and calculation to you, but those are only for your knowledge, for your information, but not for the test. The very basic, very simple calculation in the first 9 chapters, those are important. So I'm gonna make some questions based on that, and so you will see how they will look like when you have your when you have time to look at the practice test. All right, and the remaining steps are the same. So once you get the linear regression from the logit function, and then you can still do the MLE to estimate the theta and the variance theta. And then you can test whether the locus has a additive effect or the dominant effect. All right, so this is example. So here we have a categorical trace. I believe this is a study for what? For a wheat. So this is a wheat genome. So we want to see if the female fertility, this is a categorical trait, whether an individual has a seed or the seed absent. So this is 1 or 0, right? So we can use what we have learned today to do the GWAS. Still, we can scan the genome and identify the genomic region that are associated with this binary trait. Okay. All right. So we're done. So we are very quick now, right? So since we have learned the basic knowledge and theorem, so we can easily like apply those to different situations. All right, any questions for today?
I have a basic concept question.
Mhm.
So the least square estimates or the weighted least square estimates, are they all linked to the maximum likelihood estimation process?
Yes. So so I can say for most of the probability problem, so for most of the model-based problem. So for example, if you can use some specific probability density function to model your model, then for most of the situation, the MLE can give you the same identical solution with the for the least square, especially for the linear regression. And when you assume the when you assume a normal distribution for your residual error, yeah. So they are the same.
Oh, they give the same
Yes.
solution.
Yeah, it will give you the same solution. So especially good for the linear model with the normality assumption for the residual error.
Yeah, because in the lectures we see them being used simultaneously or
interchangeable. Yes, they are
interchangeably. So
yeah. So in the previous chapters, when we talk about the regular linear model, with the residual error is being assumed to be normally distributed, so that's the same. Yeah. So when we talk about the MLE and or the least square, they are the same. They give you the same solution. But but for example, if we are talking about the probit or the logit regression, so I don't think like least square will give you a good. So probably you cannot find any solution for the least square because it's not designed for that problem. But the MLE, yeah, we can always use it.
Through the EM algorithm or something, right?
Yes.
Okay, thank you, Professor.
Sure. So any other questions? Okay, very good. So I think, yeah, so in terms of the pace, I think we are doing very well. So, and so today, so I don't think we have lecture on Thursday, right? Because that's a holiday. Okay, unless you want, I'm okay. No. So my family also do not agree with this. I understand. Okay, so so we have, let's see, we have another week. How many week? We have yes. So we have 2 more weeks. So we're doing good. So and I think we have like at least 3 lectures. So the plan is like so today we finished the chapter 11. No, oh, I haven't started chapter 11. Okay, still good. So I think, yeah, we can finish everything because when you look at the lectures slides so I only made 2 more lecture notes. So the next one will be chapter 11 and 12. So we're gonna finish that one using 2 lectures, and then for the chapter from 13 to 25, we just use 1 lecture to finish those. It's very easy. So yeah, because you have already learned all the theoretical stuff. So So based on that, so when you will find that it will be very easy for you to read through all the later chapters because they're the same. We use the same schemes, all the schemes we have learned and we apply those in different situations to do different analysis. So yeah.
But do we have to read the textbook for 13 to 25?
You don't have to, but yeah, I recommend if you have time. So it's fun to read those.
Okay.
All right. Any other questions? If not, okay. So I will see you next week and happy Thanksgiving.
Happy Thanksgiving.
Thank you.
Bye. Thank you.
Bye-bye.
Bye.